Hey friends, so we're going to finish up some more NMR questions, and we're going to start off with the ones where he gives you a spectrum and you have to figure out what molecule it is. So for these ones, I have a general order to how I do them. The first thing I like to do is see how many signals we have. We have 3. So I like to just write that down. And I also, before we do anything, I also notice that all of the signals are in the alkyl region. So now I go over here and we're going to see which of these answer choices actually has just 3 signals. So first thing we look at is symmetry, right here down the middle. So we have this signal, which is exactly the same as this one. This signal, which is exactly the same as this one. No signal on either of these carbons because they have 4 bonds already. And then we have 1 signal here. Okay, 3, that works for now. Next up, we have internal symmetry here. So we have 1 signal, that's exactly the same as this one. We have a second signal here, a third one here, none here because of the triple bond, none here because of the triple bond, or 5. That's way too many. Next one, internal symmetry over here. So we have 1 signal that represents all of these guys. No signal here. We have a signal here. We have a signal here, here, and here. But we see 5 signals. That's way too many. We cross that choice out. Next up, again, we have some internal symmetry. And so this is 1 signal. Again, no signal here or here because of the triple bond. And then we have 2, 3. Okay, this could be the answer. Last but not least, symmetry again. And we have 1 signal, 2, 3. And this time we do have a signal here because there is a hydrogen coming off of that triple bond. So again, 4 signals is too many. We're going to cross out this answer choice. So just like that, we've gotten rid of 3 answers and we're down to 2. So when I look at this spectrum, there's one thing that really pops out at me, and it's this number 9, right? So this 9 is the integration of one of the signals. So let's go through the 2 answer choices we have left and see which of them has an integration of 9. Starting here, if I draw out these hydrogens, we know that there's 2 methyls that are exactly the same. The highest integration number we have is 6H, so that cannot be correct. Let's check answer choice D. We have 3 methyls this time, so that would be 3, 6, 9 hydrogens. So that is, that is a 9H signal. And then we have 2H and 3H. Let's see if that matches. Yep, a 2H signal and a 3H signal. So we can say that the correct answer here confidently is D. Ta-da. Next up, we have a similar one. The first thing I see here, again, 4 signals. And I see that now we have 2 regions. We have the alkyl region and we have the heteroatom. This kind of helps us a little bit when we're narrowing down our signals. I also see that there's an integration of 6. Cool, so those are the big pieces of the puzzle that we need from the spectrum. Let's look at the answer choices. Internal symmetry right here. So we see 1 signal, 2 signals, none here because there's no hydrogen, 1, 1. Okay, 4 signals could be possible. Next up, 1, 2, 3, 4. Okay, 4 signals could be possible. For C, we have some internal symmetry going on here. So we have 1, 2, 3, 4. Okay, this could also be a choice. D, let's cut this thing right in half. We get 1, 2, 3 signals because there's no hydrogens here. So this one has to be wrong. There's not enough signals. Last but not least, we have symmetry here. So this methyl is the same as the other one. We have 1 hydrogen here, 2, 3, 4. So altogether, we have 5 signals. So that's too many signals. We get rid of this one. So just by number of signals, we've gotten rid of 2 answer choices. And now we're down to A, B, and C. So there's a lot of different ways you can approach this one. I think that the most obvious one to me is the 6H in the heteroatom region. So that's where I'm going to start. So here I see 1, 2, 3 carbons attached to a carbon attached to an oxygen. So that's the heteroatom region. Here we have 2. And here we have 3. So first of all, this would be 1, 2, 3 separate signals in the heteroatom region, which we don't have, and it would not be a 6H signal. So this one we can take out. For answer choice B, our oxygen is here. So 1 carbon away, we have 2 hydrogens. So the signal would have 2H, not 6H. We get rid of that one. All right, C looks promising because it has that symmetry. So I'll do it in a different color. We have 3, 6H, cool. So we have an integration of 6H. And let's just double check that these are in the heteroatom region. So they're attached to a carbon that is directly attached to an oxygen. So yes, we do have 6H in heteroatom. And so for that reason, C is our correct answer. Oops, sorry about that. Alrighty, let's move on to some mass spectroscopy questions. So he might give you a question like this where he shows you a spectrum and he asks you to figure out what structure we have present. There's a couple different ways we can go about this. First of all, I like to always just find my tallest peak and label it. So we know that this is the base peak. And we know that the base peak corresponds to the most stable fragment. Not helpful in this question, just I wanted to remind you guys. Now, where some students tend to have trouble is figuring out what's the M+, M+1, M+2 kind of deal, right? And so, like I told you guys, we're going to zoom in all the way to the right side of the spectrum. We know that our M+ peak is going to be the tallest on the left, right? It'll be either the second to last or third to last one. Our M+1 is super tiny and 1 away from M+. And our M+2 could be variable, but we don't always have to have it, right? So I'm going to look at this end area, and it's kind of hard to see, but we have a teeny tiny peak here and a bigger peak on the left of it. So this teeny tiny peak is the M+ peak. Excuse me, the M+1 peak. This one is the M+ peak. And in this case, we do have another peak after the M+1 that indicates an M+2 peak. So now we're going to figure out like how the size of our n+2 compares to the n+1 peak. And if you just look at it, it looks to be about 1/3 the size, but let's just double check. So I'm going to go ahead and duplicate 1, 2, 3. Yeah, it's approximately 3 times the height of the signal. So when the n+2 is 1/3 the size of our n+, we know that a chlorine is present. So let's zoom back out. So we can automatically see the only answer choice with a chlorine is C. Now he gave you 2 answer choices with nitrogens. I guess he was trying to trick you a little bit. So how do we know if a nitrogen is present? Well, when our n+ peak is on an odd number, we have an odd number of nitrogens present. So let's see. If our n+2 is at 80, that means n+1 is at 79, excuse me, and the n+ is at 78. So our n+ peak is not at an odd number, so we can't have an odd number of nitrogens. And I would go through these 2 and tell you why they're wrong, but like it's kind of obvious that this one is the answer, so I'll leave it there. Ta-da! Let's do one more mass spec question. So in this mass spectrum, right, again, I'm just going to highlight the tallest peak, and I'm going to label it the base peak. And again, all they're asking for is for you to find the molecule that this comes from. So again, let's zoom in to this end of the spectrum, right? And again, we know we always have an n+ peak. We always have an n+1. We don't always have an n+2. And we know that the n+1 peak is always the super, super tiny one at the end. So I'm going to say that is the n+1. And we know that the n+1 is always 1 down from the n+, so we're going to say this guy is the n+ peak. So our n+ peak is at 87. We have an n+1 at 88. And we have no n+2 peak. So first of all, n+ is at 87. 87 is an odd number, so we know that an odd number of nitrogens are present since this is an odd number. So we can automatically get rid of this answer choice because it has 2 nitrogens. And then there's 2 ways I want you to think about answer choice A and B, right? First of all, you can go ahead and count the mass and make sure they line up, but also you could think there's an oxygen here. Oxygen would be represented by an n+2 peak. Since we don't have an n+2 peak, we can get rid of answer choice A, and we know answer choice B is correct. If you go ahead and do the math, you will find that this equals 87 mass units. Ta-da! So I hope you found these questions helpful, and that's about it.